Physics. Elasticity of material. We're going to look at the following outline: elasticity and Hooke's law, Young modulus, material and their types, and then finally we'll look at some calculations. Elasticity. This is the ability of a material to regain its original shape and size after undergoing a stretch or compression. Either you stretch the material or you compress the material, the ability to return back is elasticity. Okay. Next, we look at Hooke's law. It states that provided the elastic limit of a material is not exceeded, the extension E is proportional to the load or applied force F. Mathematically, we have F directly proportional to E. If you remove the proportionality sign, F is equals to KE. All right? Where K is the stiffness constant or the elastic constant. Elastic constant. If we make K the subject in that formula, K will be equals to F over E. All right? Now, elastic constant is the force required to produce a unit extension. The force required to produce a unit extension. It gives a measure of how strong a wire or a spring is. F is measured in Newton, E is measured in meters, therefore K is measured in Newton meter. Young modulus. Young modulus E is the ratio of stress to strain. The ratio of stress to strain. Mathematically, Young modulus E is equals stress over strain. Now, stress is defined as the force per unit area. Mathematically, stress is force over area. All right, we can abbreviate it as stress equals F over A. Now, the unit of stress is Newton per meter square. Strain is the ratio of extension E to the original length of the material. Okay, strain mathematically is extension over length. Strain can be represented as E over L. Now remember that strain does not have any unit. Therefore, we can also express Young modulus as follows. E equals F over A all over E over L. All right? If we rearrange it, E will now become FL over A small e. All right? F is the force, L is the original length, A is the cross-sectional area, E is the extension of the material when extended, and big E is the Young modulus of the material. Stress or strain acting on the material or body can be tensile. So we can have tensile stress or tensile strain. This is when the force acting on the body is pulling the body outwards. Okay? When the force is dragging a body outward. When the force is dragging a body outwards. That's tensile. Okay? Now, we have number 2, compressive stress or strain. This is when the force is pushing the body inwards, trying to contract the body. All right? As shown below, the forces are pushing the body, so we have compressive and tensile strain and stress. Now, types of material. A material is a substance or a mixture of substance that constitutes an object. All right? It can be pure or impure. It can be living or non-living matter. Okay? Examples of materials are plastics, metals, wood, glass, steel, paper, sand, etc. Now, based on elastic properties, we can classify materials into three main types. We have the ductile material. These are materials that show appreciable elongation before breaking. They show you sign that they want to break, they elongate, like aluminum, copper, silver, steel, and so on. Then we have the brittle material. These are materials that don't show sign. They don't show any appreciable elongation. They don't elongate like that. They easily break, like glass, ceramic, graphite, etc. Then we have the last type of material, alloy material. These are materials that continues to elongate. They are made to have additional properties than ordinary metals or materials. Okay? Examples are the brass, the bronze, the steel, etc. Strained elastic wire. The graph of load against extension for a wire which has been stretched gradually until it exceeds its elastic limit is shown below. But before we show the graph, let's explain a little point. Now, within the elastic limit, Hooke's law is still obeyed. The point where the material, when you add a load, it stretches and return back. Okay? Beyond the elastic limit, the wire stretches permanently. And if the load is removed, the wire is found to have been distorted, it cannot return back. If the load on the wire is increased further, a point will be reached where a small increase in load produces a large extension. This is called the yield point. Okay? If we continue to add load, a point will be reached when the wire will break. The wire will break. So you are adding load to a material gradually, and the thing is extending and extending until it gets to the breaking point. That's what we are saying. The graph is shown below. Graph of load against extension. When you add load, a small load, it will extend. When you remove the load, it will return back. That is within the elastic limit. Above the elastic limit, if you add a higher load, it will get to a yield point where when you remove the load, it cannot return back. The material is strained already. As you continue to add load, it will get to the maximum load and then it will now break. Energy stored in an elastic spring or material. The energy used up or work done when an elastic material is stretched or compressed is given below. The force is acting on the material and the force is F. Then the work done is given as W equals half Fe, force times extension. Or we can also say W equals half Ke square. Any of the formula can go. Let's look at some calculations. Example 1. A spring of natural length 5 meter is extended by 0.01 meter by a force of 6 Newton. What will be its length when the applied force is 12 Newton? Solution. First, we have our parameters intact. We first use our formula F equals to Ke to find the elastic constant first. F is 6 from the question. K times the extension 0.01. If we make K the subject, we have 6 over 0.01. Okay? If we divide, K will give us 600 Newton per meter. All right? Using F equals to Ke again, this time our force will be 12. Okay? And then K is 600. We're looking for the extension E. Okay? Divide and make E the subject. We have 12 over 600, which will give us 0.02. Therefore, our length will now be 5, the original length 5 plus 0.02, which will give us 5.02 meters. Example 2, a wire 2 meter long and cross-sectional area 0.0001 meter square is stretched by a load of 80 Newton. The wire extended by 0.001 meter. Calculate the stress, the strain, the energy, and the Young modulus. First, to get the stress is equal to force over area. The force is 80, the area is 0.001. When we divide, we're going to have 8 times 10 to the power 5 Newton per meter square. For strain, we use extension over length. The extension is 0.01, okay? 0.001 over 2 will give us 0.0005. If we change it to standard form, we're going to have 5 times 10 to the power minus 4. For the work done or energy, we can use half Fe. So 1 over 2 times the force, 80, times the extension, 0.001. So when we multiply, we're going to have 0.04 joule as our work. Then finally, for the Young modulus, we use E equals stress over strain. All right. Now the stress is 8 times 10 to the power 5, and the strain is 5 times 10 to the power minus 4. All right. 8 divided by 5 will give us 1.6 times 10 raised to the power 5 minus 4. Minus will give us plus. So we're going to have 1.6 times 10 raised to the power 5 plus 4, 9 Newton per meter square. Now, we are going to do the following exercise. Right, number 1, a spring of natural length 3 meter extended by 0.01 meter by a force of 4 Newton. What will be its length when the applied force is 16 Newton? Number 2, just follow the example and study the exercises very well. You'll be able to solve them easily. All right, number 3, mild steel wire of radius that and so on. So in number 3, you're looking for the extension and the stress. Calculate the stress, the strain, and the elongation. Is that okay? All right, for more of our videos in this channel, please don't forget to subscribe, and thank you for being a part of this class.